This is the first lecture on type reconstruction. So we will have 2 lectures on type reconstruction, and this is the first one. So let me first summarize the story so far. We started with system F, which is very expressive, but its type reconstruction is undecidable. This is very expressive, but type reconstruction is undecidable. And then we considered predicative polymorphic lambda calculus, which supports polymorphic expressions, but it's not quite expressive. And in fact, it's not expressive, almost to the point of being useless. But the type reconstruction is decidable. So after comparing the 2 systems, the system F and predicative polymorphic lambda calculus, we want to find some system that lies between these 2 that offers sufficiently expressive type system, so sufficiently expressive, and it maintains the decidability of type system. So we learned that let polymorphism lies at this sweet spot. It offers a good compromise between this predicative polymorphic lambda calculus and system F by inheriting the best of both worlds. It's reasonably expressive because we can define polymorphic expressions and we can use polymorphic expressions really polymorphically in different contexts. And it also inherits decidability from predicative polymorphic lambda calculus. So we wanted to use this let polymorphism as the basis for practical programming languages. And at the next step, we introduced this implicit polymorphism as the real foundation for practical programming languages. In the case of let polymorphism, everything is explicit. The expression, the user should actually declare type variables, but that's quite cumbersome. So in implicit polymorphism, we get rid of type annotation. So we don't have a type annotation. In the case of let polymorphism, we have this form of lambda abstraction with type annotation. And implicit polymorphism just removes type annotation, and we have this form of lambda abstraction without type annotation. And in the case of let polymorphism, we also have this type abstraction, which explicitly declares type variable and also type application. But these guys are gone in implicit polymorphism. So in the case of implicit polymorphism, polymorphic types arise from the lack of type annotations. And another noticeable change when we transition from let polymorphism to implicit polymorphism is, in the case of let polymorphism, we have this introduction rule and elimination rule, because we have this type abstraction and type application. But now, in the case of implicit polymorphism, we don't have this type abstraction and type application. So these guys are gone. So these 2 typing rules are rewritten into this generalization rule, the generalization rule, and specialization rule. The generalization rule says expression E has for all alpha u if we declare this pressure type variable alpha and expression E has a type u. So this is generalization rule. And the specialization rule says If expression E has this polymorphic type, then we may instantiate this type variable alpha with A, monotype A. And we also have to make sure that this A is a valid type, so we use a type judgment. A is valid type. So this judgment says A is a valid type. So implicit polymorphism employs this generalization rule and specialization rule instead of this for all introduction rule and for elimination rule in lab polymorphism. So now we are ready to develop a practical type system based on this implicit polymorphism. Now, the problem that we'd like to address is type reconstruction in this implicit polymorphism. Type reconstruction. So remember that in this language, implicit polymorphism, there's no type annotation. It's your responsibility or the responsibility of the compiler to figure out the best type that can be assigned to this variable x. So, for example, the type reconstruction problem could be formulated like this one. The problem is you are given a program E or an expression, closed expression with no free variable. So this is a closed. So therefore, you can think of it as your source program. And then this is the input. And then the output is going to be, we'd like to find the best type that can be assigned to this expression E that satisfies this typing judgment. So in other words, we'd like to reconstruct or infer by analyzing the expression E, and then we'd like to figure out the best type that can be assigned to this expression E. So this is the problem of type reconstruction for implicit polymorphism. And later we will make the statement more precise, but here we want to remember the fact that this type U must be the most general type that can be assigned to expression E. So here's an example. Let's say we'd like to find the type for this identity function. And this type reconstruction algorithm can return, for example, bool arrow bool. This is a valid type that can be assigned to this identity function, or we could return int arrow int as an answer to this problem. So the problem is, what is the type of this expression? And the answer could be this bool arrow bool, int arrow int. So these types are fine, but it's not really the best answer that we can find, in that we can have actually the most general type, which is for all alpha, alpha, arrow, alpha. So intuitively, this is more general than the previous two types because by instantiating this type variable alpha, this can be specialized to any of these two types. So to summarize, although these two types are fine, they are not actually the best. This is the best answer that we can find for the given expression, in that this is the most general type. So the algorithm for type reconstruction, our type reconstruction algorithm should return a polymorphic type for all alpha, alpha, arrow, alpha for the given expression like this one. So we will later make this statement more precise, but for now, let's remember that the type returned by the type reconstruction algorithm is going to be the most general possible type that can be assigned to given expression. This is not the answer that we want from this type reconstruction. This is the answer that we'd like to see from this type reconstruction algorithm. So now we are almost ready to develop the type reconstruction algorithm, but we can make another small change to these two typing rules, because when we actually develop this type reconstruction algorithm, we will have to introduce lots of type variables. For example, whenever we apply this generalization rule, we will have to introduce this type variable. So we will introduce lots of type variables, but we are not testing a solution to this problem submitted by somebody else. So in other words, we are not testing whether a solution submitted by a student is correct or wrong. We are not checking the validity of a solution. Rather, we are developing a new algorithm that will automatically find the best answer. So in the course of this type reconstruction, there's no reason to generate invalid type variables, simply because it's just nonsensical. There's no reason to intentionally generate invalid type variables in this algorithm. So in other words, the type reconstruction algorithm that we will be developing is going to generate only valid type variables, simply because there's no reason to generate invalid type variables. So with this assumption in mind, we can say that every type variable that appears that is generated by this type reconstruction algorithm is going to be valid. So therefore, now there's no reason to state explicitly this alpha type variable alpha is valid, because we assume that every type variable is valid. So this will be gone actually. And for the same reason, we don't have to actually test the validity of this type here, the type A here. There's no need to check the validity of type A here, because we assume that every type variable is valid. So for instance, this type A might contain some type variable, say beta, gamma, and so on. And previously, we had to make sure that these type variables are valid. But now, because we are developing a sound type reconstruction algorithm, there's no reason to intentionally generate the wrong type variables. So these type variables are guaranteed to be valid. Therefore, there is no reason to test the validity of this type A, because everything is valid anyway. So we make another small change here. This is going to be this is going to disappear, and we remove this one. So let me rewrite this generalization rule and specialization rule. So we use implicit polymorphism, where the generalization rule has been rewritten as gamma E has for alpha U, where expression E has a type U. Now, suppose that we have type variable alpha. So previously, in the original implicit polymorphism, suppose that we explicitly introduce type variable alpha here. Now, in designing this type reconstruction algorithm, there's no reason to explicitly state this validity of type variable, because every type variable is valid. Now, suppose that expression E has a type U. Now, alpha is not found in type variable gamma, but alpha is found inside type U. So for example, U could be alpha arrow alpha. So what does that mean? So it means that from these two conditions, alpha is not found anywhere in gamma, but alpha appears in the resultant type, the type assigned to this expression E, then we can deduce that alpha can be considered as a fresh type variable introduced by this generalization rule. So if this is the case, you are permitted to introduce for all alpha. And formally, this condition is stated as alpha is not a member of the set of free type variables of typing context gamma. So the formal definition of the function free type variable is straightforward. Basically, you collect all the free type variables from typing context gamma. So the revised generalization rule goes like this. Under typing context gamma, expression E has this polytype U. And in addition, because we want to actually generalize type U to this polytype, you have to make sure that alpha is really fresh. By satisfying this condition, alpha is not found inside this typing context gamma. So for example, let's consider this lambda x dot x. So the typing context is empty, and we are type checking this lambda x dot x. And at this point, you have to make a guess. So for instance, let's assume that we assign type variable alpha to variable x. And then, so here our guess is x has a type alpha, where alpha is unknown yet. Then this variable x has a type alpha, so alpha arrow alpha is, we can assign alpha arrow alpha to this lambda abstraction. So this is fine. Now, let's analyze the typing context and type variable alpha. Alpha is not found here. So in other words, alpha is not a member of the set of a free type variable of empty typing context simply because alpha is not found anywhere here. So we satisfy this condition. And alpha is found inside the type of this expression. So perhaps this is the best place where we can apply this generalization rule. So we apply generalization rule, and then we deduce lambda x dot x has type for all alpha, alpha arrow alpha. So intuitively, this is the most general possible type that can be assigned to this lambda abstraction. So this is one example of using this generalization rule in a proper way. And of course, your guess might be wrong. For example, you might choose to assign type bool to this variable x. So this is fine. In that case, we assign bool arrow bool to this lambda abstraction. So if this is the entire program, there's nothing wrong with this assignment. But in the case that we have a surrounding outer context, for instance, later we discovered that this lambda abstraction is applied to integer 0. So for example, this guy has a type int. In that case, our guess is wrong here. Our guess was perhaps we can assign type bool to this variable x, and this lambda abstraction has a bool arrow bool. So far the story is okay, but later we discovered that the actual argument failed to match the type of this formal argument bool. So this is not equal to int. So later the type reconstruction fails. So this is a wrong way of applying type reconstruction algorithm. You don't want to choose a specific type like a bool when you can actually leave the answer when you can actually leave the question unanswered. Or here's another example. You might be lucky. So for instance, this time we assign integer type to variable x. Okay, so then x has a type int. So the lambda abstraction is now assigned the int arrow int. And later we discover that this lambda abstraction happens to be applied to integer 0. So we are lucky. In this case, the whole expression has a type int. So everything is okay. Nevertheless, you don't want to build type of this lambda abstraction in this way. This is a really bad way of applying type reconstruction, because even though this is just a lucky case, even though the whole expression type checks with the value type integer, you always wanted to generate the most general type. If later you have to specialize the type variable alpha, you can always rely on this specialization rule. Specialization rule goes, if expression E has a for all alpha u, then you can always specialize the type variable alpha to a concrete monotype A. So you can always apply specialization rule. So it may look less efficient because you have to first generalize by introducing polymorphic type, and then you apply generalization rule to convert it to integer arrow integer. But this is the right way to build the type of the given expression. This is not the right way, even though in this particular example, we were lucky and the whole type reconstruction happened to be completed. But this is not the right way. So to summarize the story so far, we'd like to use implicit polymorphism as the basis for the practical programming language. And in order to take advantage of the fact that this type reconstruction algorithm never generates wrong type variables, we make a slightly modified typing rules. This is generalization rule and the specialization rule. And this generalization rule tests if the type variable alpha is not found in typing context gamma. So usually you collect all the type variables in alpha, so in this polytype U, and then check if they are found in typing context. And if we find such a type variable alpha here, then you apply generalization rule. And you want to apply this generalization rule aggressively in order not to fall victim to some funny situation like this one. And in the case of specialization rule, now you don't have to actually test the validity of this monotype A, because by assumption, this type A is guaranteed to be valid. So for instance, you might introduce fresh type variable when you apply specialization rule. So you might introduce actually fresh type variable beta, but that's fine because beta is assumed to be valid. So we will